What's up, everybody? Peel helping out Dylan right there. Dylan's got some questions about Shiny, making some cool stuff. It looks like the vote is left arrow. Dylan, 100 points. Everyone's voting some left arrow right there. Is this chi-squared? When the population, mean, and standard deviation are known, what distribution you use? So Warren, good question. So have you heard us talk about, what do people think? Have you heard us? Morning, Leo. Great to see you here. We haven't had too many bumps. I've had a problem with the, wait, let me answer Warren's and then I'll tell you. Have you heard us talk about the chi-squared yet? Have you heard us talk about the T or the chi-squared distribution in class yet? So good question right now. We can go to some Pearson questions, whatever people are wondering about. Have you heard us talk about the chi-squared yet? Has anyone heard us talk about chi-squared in the chat? Has anyone heard us talk about chi-squared? We have not talked about chi-squared yet. I might have said it by accident. I've never heard of it. Chi-squared? What you talking about? Well, if I did, I might have said it about something or some reason. I don't know. You have heard it? Oops. So when the population mean and standard deviation are known, what distribution would be used? Let's go to the look at this. So it's talking about this right here. When the population mean and standard deviation are known, what distribution would be used? This is a great... No. Wait, that was X over N? Which thing? When the population mean and standard deviation are known, what distribution should we be using? When the population mean and standard deviation are known... Put some gel in my hair. Carbon monoxide, you got it. What is that here next? Briley, great question. When the population mean and standard deviation are known. Carbon monoxide. When the population mean and standard deviation are known, what distribution should be used? Who knows in the chat? The population mean and standard deviation are known. That's this slide right here. If the population mean and standard deviation are known, so what it's telling you is, I'll highlight it. It's saying the population mean is known. That's that. And the population standard deviation are known. Normal distribution. And great job, the normal. Rather, it should talk about meeting the conditions. Like, it should, if the question was a perfect question, it would say, when the population mean and standard deviation are known and the three conditions have met, then the distribution could be described as a what distribution. So you would know the population mean, i.e. this down here, and the population standard deviation would be used to calculate the new standard deviation. Are these slides posted anywhere for someone? Yeah. 2 seconds. If you want, Dylan, here, I'm going to save this. I'll send it to you right on Discord. Here's my notes from today, Dylan. I'm going to send this right to you on Discord. And whatever you need, Dylan, let me know. So let me go over to Discord. Send this to you real quick right here. Hello! And let me send this. Here you go, Dylan. There's those slides right there, right for you. Feel free to ask for any slides on any topics. Let me know. We're more than happy to share the 201 slides. Briley's got some good questions right here. But how's everyone doing right here? Everyone having a good day? Got some nice relaxing music on. We're gonna jump into it. Ha ha ha. Second cup of coffee. Good stuff. I ran out of cream. Well, I did run out of cream, but I had enough. Different distributions. Different questions. I'm doing good, Hunter. Good to see you here. 100 points. It's like depending on the question you're asking, whether it be quantitative, categorical, whether it be defects, whether it be discrete data. There's a lot of good graphics online, and someone should walk through. Man, I should make a video on 201, like every distribution and when to use it. But there's a lot. It'd be a good video. Like sometimes I think about making a video that could go viral and be like every distribution and when to use it, every statistical distribution and when to use it. But I probably missed some. Like there's like the Cauchy, the Poisson, is it the binomial, the negative binomial, the Pareto, normal T, chi-squared F. I'm trying to think of any more I can think of off the top of my head. I should think of more. Shapiro-Wilk, W. There's a whole bunch. There's a ridiculous amount of distributions. Everyone just makes up their own distribution, their own name. We're pulling up the carbon monoxide question as we talk right here. That should make, I probably could make a video. Problem is I know how to use most of them. I don't know how to use every single distribution that exists because there's some I don't know. Chapter 14, Pearson, you got it, Kyle, right there. Kira, we're about to do the carbon monoxide question, but drop more questions in the chat if you got them. Carbon monoxide question is coming up here in about 20 seconds. Got it loaded up. Just getting the new timestamp and typing the time in the video. It's about 7:15 in, and stat 201, chapter 14, carbon monoxide. Here we go. Let's do it. So here we are with the carbon monoxide question, chapter 14. Got my dragon fruit Red Bull. Ooh, it's a good start. Ooh, Lou, I don't know if I've had that. Maybe I need to go buy that. So what's the first thing we do? Great work. See, and go do some 14 forward, Dylan. You got this. What's the first thing we do with a problem like this? If you get a problem here talking about the carbon monoxide of cars, the first thing you should do for any sort of problem is do what? The first thing is don't click on your Streamlabs. The first thing you should do for any of these problems is you should do what? This could cause issues. I accidentally clicked Streamlabs OBS. The first thing you do with any of these is do what? Good deal. You could check conditions. It might have you go through and look at the conditions. That's a great answer, Briley. I would do some notation, brother. Sounds like some Hulk Hogan right there or something. So like do some notation, I would say. Mark your notation. This is also going to help you know which formulas to use. So does anyone know any of these values right here? I'm going to color code them. Any of these values right here. And these are the values to know. It's talking about we have a fleet of 60 cars. They have a mean of 2.0848 grams per milliliter of whatever carbon emissions it is, and a standard deviation of 0.7 grams per I don't know what that is. G over MI, or it's an MI, I think. It's an MI. N is 60, correct. That is the sample size. Sample size is 60. Now, be careful when you tell me the other ones, because there can be confusion. Yeah, do some Q4C. You bet. I'll put that on the list right here. Thank you, Thacker. So you're wondering about Q4C, assignment 6 for 474. Yeah, let me put that on here. And 201, ask more questions. Here we go. BSR 75, Q4C. There you go. Got it on the list. You bet. What else do we have right here? Briley, that is correct. You're welcome, Thacker. That is correct, Briley. We're going to do the standard deviation of the square root. So what is the standard deviation? 0.7 is not the sample mean. Good, Leo, good work. 0.7 is not the sample mean, though. 100 points. 0.7. Oh, wait. Oh, kind of. I see. So I see what you're saying. I see what you're saying. I think you're on the right track. And this is where usually mistakes are made. 0.7 is sigma. You will use that. I think I know what you're saying. You'll use that for the standard deviation of the sample mean. Correct. That is the original standard deviation. And then this is the original mean, mu. And the notation, once you get this, the rest of the problem just flows from this. So you have to get the first initial notation, because then we're just going to solve for the mean of the distribution of the sample mean. And what is that equal to? So now the question gets a lot easier once we know this, because the mean for the distribution of the sample mean is equal to what? What is the mean for the distribution of the sample mean equal to? From here, it's just like, oh, we'll just go boom, 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 boom. The mean for the distribution of the sample mean is equal to what? I think they're roofing out there. 2.048, that is correct, is equal to mu. And that's 2.048. That's all it is. Solved. It's just the mean. It's what we would expect on average from a sample of this size. The size here, Rock knows. It doesn't matter! Because it's just the mean. But the standard deviation for the distribution of the sample mean is going to get smaller by a factor of the square root of n. So we take the 0.7 and we divide by the square root of 60. Does anyone have it for me? Does anyone have the new standard deviation? 60 square root. And it doesn't matter what's in here. There we go. 0.0904 equals There we go there. 0.0904. 0.0904. So that is 0.0904 right there. And so let's go back over to here. Look at the question. So we're going to use not a Poisson, not a binomial. We're going to use the normal distribution. And we're going to go right here and do the standard deviation down to 3 decimals. There it is. And the mean is going to be 2.048. And that should be it for that question. Now, here's the thing. On your own, if you can't solve this, what do you think Brian would need to do right here with this information? On your own, if you're working a test problem, what are you probably going to have to do with the mean and the standard deviation? On your own, what would you need to do? What would you need to do on your own? What would you need to do on your own right here with the mean and the standard deviation? Draw the distribution. So on our own, we need to draw the distribution. What value is going to go right here? Great job, Hunter. Draw it out, right? Right there goes the mean of 2.048 because that's the mean of the distribution. You might be given pictures of the applet, or you could have to solve, like it might say a sample mean of 2.35 is this, or let's make it even bigger. So tell me, be careful, this is a tougher question for people. Is this sample mean right here unusual, yes or no? Is that sample mean unusual, yes or no? Is that sample mean? It's just practice. We got this, Warren. It's just practice. Is that sample mean unusual, yes or no? So Leo says yes. Leo, can you justify that answer? Don't worry, Leo. I'm trying to see. Not that you got it wrong. But Leo says yes. Warren says yes. Why is it unusual? So can you tell me why it's unusual? You might be right. But wait a minute, Leo, the standard deviation. Great to see you here. We got a friend here. Awesome work. The standard deviation is this, though, Leo, right? Wait, correct me, Leo. Correct me. And Briley's saying it is unusual, too. I'm trying to trick everyone, so don't worry right here. This is the error people make. A lot of people use this standard deviation up here. What is the standard deviation? We have the new standard deviation right here is the one we should be using, right? So what could we find for this? Like, even if we don't draw out the applet, what could we find for 2.45? And this goes to the test. And good to see our friend here. You earned everyone some huge points, 500 points. Everyone's saying thank you. If you missed the video last night, we threw out some great points, and we appreciate all the positivity. So we could find the what for this observation. We could find its what. So we could take that observation right here, plug it in, and we could find its what. So this is the observation's distance from the mean over the standard deviation. This formula will find a what right now for it. Find the z-score. Correct. That's going to find its z-score right there. Exactly. Kyra, great work too. The z-score. This is also on your formula sheet. So this is the z-score. And this would be a very unusual observation if you plug in the value of a sample mean of 2.45 minus the mean of the distribution, which is 2.048. Boop. And then over the standard deviation, we found the new standard deviation is 0.0904. It's something like 4-ish standard deviation is 4.2 maybe. So we take, there's random noises and sirens outside. I love it. I don't. 4.44. 4.44. 4.45. So that would be very unusual. So what we want to do now is we want to go to David M. Lane applet, which we don't have access to on the test, but we can always draw these things out. We can always find z-scores. On the homework, you will use David M. Lane. So here we go. David M. Lane, pulled up in the chat. We're going to take the mean of the distribution, which is, I'm going to go find that mean again. The mean is 2.048. And we'll put in the mean. Standard deviation was 0.0903. And now we need to go here. It's drawn our distribution for us. and with the distribution drawn. And if you have more questions, put them in the chat. It says, what is the probability between 2.1 and 2.3? We go between 2.1 and 2.3. There's the answer. We're literally just going to copy paste it into here. And then it says, what is the top 10% of cars? So the top 10% of cars. Could you possibly do the first capture? Yeah. What's the first one say? Jameson, can you put in? We'll do that after the 475 question. What's the question say? And I'm taking the values and putting them over here to get the top 10%. So it wants the top 10%, and that's going to be 2.2 rounded to 1 decimal. If you put it in the chat here, we'll solve it here after the 475. You got it. So those are just found via the applet. Please take a moment and saw how I was using the applet to find the top 10% with the second button. So here's how to find the top 10%, which is the last question. And then here's how to find the area between two numbers right here. That's between the numbers. The pregnancies, you bet. The pregnancies, Jameson has one also. I'm taking a list of the questions. So we got Stat 201, Chapter 14, pregnancies. And then Jameson's mentioning another one from Chapter 14. And let us know. We should get 100. Cross your fingers. Not today, my Pearson. What? Do you see it? This is one of those ones you need to email me on. It's about the waiter tip? You bet. Let me put the waiter tip. Who sees the error? Who sees the error? Who sees the error here? I got that 100. You can email me and say, Brian, I got that 100. Rounding. My music is messing up. It's a sad day. Rounding. Sad day. Email me if that happens to you, and you will get your points back. Let's go back here. We got more to do. Sometimes my that thing is making broopy noises. Maybe I need to reset or update the firmware on it. It's dark today. Okay, we're gonna do some 475. If you're 201, hang out. There'll be more. Let me get the assignment open over here. Heading over here. Checking everything out. The question was 475. And so good to see you here, Briley and Jameson and Christian. Great to see you here. It was 475, Q4C. Q4C. So is it the stationary one? Stationary. Okay. Let's go ahead and get... Let's talk about how to talk about some stationary data. Assignments. Grading should be caught up for the class here soon. We've got some ARIMA and exponential smoothing. Downloading assignment. Taking the new timestamp. Great to be here. Awesome, Jameson. How did you find the 10% on the applet? The second button, we can go back and Kyra, good question. Click the second button and put in the top 10%. The second button and click over to the top 10%, Kyra, right there. Here, I can show it again. I got it on the screen still. If you take a look behind me right here, make sure you've clicked the second button, put your mean, standard deviation, and then you can find the top 5%, top 1%, top 2%. Make sure it's showing you the top such and such percent. Make sure you have the proper mean, standard deviation, be on the second button, which allows you to put in the area, and then you could find things like the top 20. Does that make sense? Thank you, Leo, also answering the chat. Great work, Leo, helping out. 100 points right there. And make sure it's the second button, though. You didn't know the Marvel screen could disappear. Magic. Great work right there, Kyra. Good work. And we are going to be doing more 201, so stay tuned if you're a 201er. We're doing it next. Here we go. Not next, but... Okay. So what you're seeing right here is some time series. If you're 201, this is... Oh, I got the wrong thing clicked. Did not get increase that. There we go. So the start of this is looking over some Amazon stocks, I believe. We've got the GAFA stocks, which is Google, Amazon, Facebook, and Alexa. I don't know. Just taking here, plotting some data. Oh, it's mad at us because we don't have FPP3 loaded up. So let's get everything loaded up right here. There we go. Now we can look at some GAFA stocks. There, oof. If you are in our class, if you're in 475 and you see this, what is this down here? What is this pattern right here indicative of? Now, what's interesting, if you're 201, you'd say, I've never seen anything like this. But this C you've probably heard of. This C stands for correlation. And this is the partial autocorrelation function. This is the autocorrelation function. So you've heard of this C before. And the correlation is very, very what in this data? And we're talking about auto, which means self-correlation. So the correlation looks to be very, very what? Because think about the values of correlation, and you might see this. The correlation is very, very what? It's not too bad, Leo. This is very, very what autocorrelated data. It's very, very high autocorrelation because correlation only goes to -1 or 1, right? And so this has very, very strong autocorrelation. And think about this. This means, so this kind of goes to finance. Yesterday's stock price is highly correlated to today's stock price. Like if yesterday the stock price is low, today it'll probably be low also. Now, we're not saying it will be, but if you want to know what the stock price is today, yesterday is a pretty good indicator. It's ground-shaking knowledge, groundbreaking knowledge to say yesterday's stock price is highly correlated with today's stock price. That's what we really learned from this. Now, also, there's this pattern here. This is indicative of a trend. Trended data will have an ACF that kind of goes down very slowly. These blue lines represent statistical significance, so there's highly significant autocorrelation among the data. The PACF cuts off right here, but we're more concerned with this ACF having this constant dip. This data needs to be differenced. Hopefully you knew that. That would remove out the trend, differencing detrends data. We're speaking more specifically down here at 4C, though. Let's go to 4C and look at that one. Are the data stationary? Now, stationary data is something easy to understand. It's basically randomness. It's kind of like the residual plot for our upcoming test in 201. We want to see a random looking data set. So which data are we working with? Choose a series from U.S. employment. Okay, so I'm not going to use U.S. employment because I don't want people to copy. Brian always does different but similar work. I swear they're roofing or something out there. I'm not going to use U.S. employment. I'm going to use OS production or something. OS production has different series right here, like if they're making cement or gas. This is the production in Australia. What do you think we should pick? Beer, tobacco, bricks. This is all the production in Australia right here. By each quarter, their quarterly productions. Should we look at cement production, bricks production? What is the votes in the chat? And the first person to say, should we look at beer production, electricity, gas, oil? Do we have oil? Is that, wait. Ali mate? Oi mate? I read that as oil. I don't know. Beer. Hunter's chosen beer. Okay. What's really nice is the auto plot. I don't know if it asks us to auto plot. It does us. It says a decomp. We won't do the decomp. Beer not found. What? There we go. Is this stationary data right now? Just looking at this right here. Is that what the question wants us to do? Let me do the question. Full thing. Okay, so we need to difference the data. Well, but that has... Okay. Produce an STL decomp of the data and describe the trend and the seasonality. Okay, so let's get an STL decomp of it. Okay, let's go get an STL decomp. I always cheat a little bit and go grab it from the book. So... Oh, I literally had it right there. Here it is. STL decomp. Is grab this, OS production, beer, boom, boom, boom. There it is. Okay. Here's our STL decomp. And what do we see by this? So a decomp takes this series and breaks it down to its components. The first part up here is the trend cycle. It doesn't say cycle on it, but it's trend cycle. Good to see you here, Ashton. Then we have the seasonality, which is the quarterly pattern. So you see a 1, 2, 3, 4 spike pattern. And the remainder for 201, what do you think the remainder is? It's another R word for chapter 7 and 8. The remainder is what is not explained by the model, or if the model's making predictions, it's how much it misses by. So the remainder for 100 points, who knows what the remainder could also be called? Because if we have the trend component, the seasonal component, and then we have what is not explained, or what we would miss by if we didn't use that in the prediction, it could be called the what of the model. And good stuff for all our classes is like, well, that's basically a what. It's how much the model would miss by if we made predictions using this and this. The remainder would be the miss of the model if this is going to make predictions. So the remainder could be called the what of the model of a trend seasonal model. Another R word, which is the actual minus predicted. This is like the misses down here on the bottom. Does anyone know? Oh, I'm on top chat still. No. Trying to pull in some 201 questions in here, or 201 things to pull into our memory. Not probability, it'd be the residual. Like the remainder, the residual. So it says remainder behind me over there. It's the residual. It's what's left over. So if you were to make predictions using this and this, then putting these back together, you would miss by this amount. So there's the, no, it's a good practice. This is 475 right here. So you just have like the trend cycle, which is kind of like the flowy pattern through it. Then you have the 1, 2, 3, 4 seasonal pattern, which is a quarterly pattern. So that's the seasonality of it. And you can see it up there in the original data up top. And then down here, you have the remainder, which is like the unexplained, not accounted for by the trend and the seasonal pattern. So there's definitely a very strong trend to this. We can talk about that there. Does the data need transforming? I don't know. We can try the box Cox. So box Cox transformation. Let me go grab that to find the box Cox lambda. 2 statisticians ran the box Cox transformation. So let me go get the box Cox transformation code right here. And does it need it? Here it is. So this will get the lambda. I'm going to love it when they're roofing our apartment. Let me go grab OS production. We're doing beer. And let's pull the value of lambda. And so that is going to transform it. So then let's plot it. And let's see what we get. Okay. And so let's go ahead and grab. There we go. Transform beer. And I mean, I'm thinking, what is your thoughts on transforming this, Hunter? We're going to do the last one here. I would show both of these. What are your thoughts on, here's the original data. We'll do a plus. Can we do plus GG title on this? Oh, I mean, your thoughts on this. Here's the transformed data. Here's the original data. Transformed data, original data. Transformed, original. I would show these. You could do a GG arrange on these probably. So let me go to this. P1 and P2 and GG arrange. What is GG arrange in? GG arrange is in arrange multiple GG plots. GG pub R. And that right there, be careful. I might even screenshot this. So here's, I would screenshot this, maybe just drag and drop it. So Hunter, this right here, what are your thoughts? Here's your original data. There's your transform beer production with a lambda value of 0.35. What are the thoughts on this? So the reason we transform data is we transform data to fix linearity issues. We also transform data to fix issues with unequal spread, which is plot thickening for 201. So are we seeing, from the original data to our new data? And this is how you justify decisions. If I want to make something clear right here, you have to look at both of these. You have to say, Here's my original data. Here's my transformation. So Leo, if you're still watching, do you think we should do a transformation right here? Why or why not? Transforming is when you multiply your values by something, kind of sort of like you're going to change the y value, be like, let me square it, let me log it, let me, inverse it. So here's the original data. Here's the transform data. We use transformations to fix issues with linearity, with unequal spread. So we're trying to fix things. We're trying to make it look like a linear pattern with equal spread, kind of like we do in Toolon, where we're saying some QQ straight enough, no outliers, plot doesn't thicken. We want to make something we can actually make a model for by transforming the y variable to something that we can work with. So would we use a transformation here or not? I think it's a question if you think about it, especially... So here's the thing. So Leo, let me ask it this way. You're thinking maybe we could because the data is not linear, right? Here's the best we could do. So if this is the best we can do, so Leo, you're on the right track. Leo, I'm throwing you 1,000 points. Since this is the best we could do, Leo, should we use a transformation? So Leo, this is the best we could do. Here's the original data. Here's the best I could do with a transformation. Do you think I should use a transformation? So here's the original data. Here's the best I could do. There's you can actually see a slight improvement to heteroscedasticity. I'm saying slight, like, so do you think I should use a transformation? Here's what I had originally. Here's the transformed value. See how y is a different number over here because I've transformed it. That's Leo, that's exactly it. It's like, well, we didn't really get what we wanted. Some transformations will fix data drastically, and you will see he shows it in the book right here. I'll show because he does such a great job of walking through these. Let me show you what a transformation should do. So here is the original data, and notice how it's not linear. And what we're doing is we're trying different values of lambda, and we might be able to make it more linear and fix it. So if you notice right here, we're getting a little bit more linear. Like there's bad values of lambda. I think can't remember which one he chooses, but you might get more of a linear pattern right here where it's equal spread. No worries, no worries. But this is the point right here, Leo, is that like we might be able to achieve a better, more linear pattern by transforming the y value. And it might be, I think his optimum value is somewhere in here. And then you have a bit more of a linear pattern. You have a bit more equal spread compared to, I think, lambda of 1's like no transformation, where there's unequal spread. Here's plot thickening, and there's non-linearity. But if you go down here to this value of lambda, you might have more linearity and more equal spread. So in this instance, we would say it improved. Yeah, the waiter, we got that one coming up here in just a moment. Great question, Sally. So Hunter, we would say there's really not an improvement right there, and I don't know if a transformation could be justified. Are the data stationary? If not, find an appropriate differencing. So the data are not stationary right here. And let's look at some differencing of this. So let's go to the differencing of, and you got it, Sally. We'll be doing that here in a moment. Os production. And it is differencing that, but it might have destroyed my tibble. And autoplot. It's mad at me. It's mad at me. Let me go see how he does it in the book. Because tibble's got to be used. And that's different. I'm pretty sure... Oh. Alexa's talking, I think. Here we go. ACF. Wait, he does the difference right there. Difference. Really? How did I not know that? Okay. So let's go ahead and take that. There's codes that need to work right there, so you take the difference of it right there. Let's go ahead and take, it's just the difference of it. Okay, so we want to take our original data, OS production. Oh, it's a Tisbol thing. It's a Tisbol. You're not found? Did that keep the Tisbol? Let's take this and try to auto-plot it. 2 seconds. 2 seconds. We should be able to take... Oh, you put in the difference number. Okay. So... let's not use a box cock. So let's just go here to the beer. And then you pipe it through a difference. Okay, you better work. Oh, no. It needs to be with inside here. Is it second? No, it's not second argument. Take the... Oh, that's the one thing is piped through. So really? Let's try that. Gonna like it. Gonna like it. There we go. Whoa, cool. Wow. Okay. Hunter, wow, what is this? What? That's so cool. I haven't actually seen that plot in a while. What's doing the GG season is what it's doing. Hunter, what are we remaining with up here? This looks mostly stationary to me, except for what in this data? If you go back to the original pattern, it's quite clear. We've been working with this beer data the whole time. We're doing 201 here in about 3 minutes. Hunter, I would say this data is mostly stationary, except for what right now? There's definitely, and this is beer data. And you can see it down there, and you can see it up here. This data is mostly stationary, except for what? This data is mostly stationary, except for what? I mean, it's not stationary yet, but we've removed out the trend with the differencing. I would say differencing of 1 is fine. Try to double difference it. The ACF looks a little bit cleaner. I might difference it twice. Yeah, that's some good stuff. So, or Leo, do you see what's still left here? What is still left in this data that we have not accounted for? We have not accounted for the what in this data. Because random. It looks like it goes boop, 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 boop. Does anyone know for 500 points, what pattern have we not accounted for in this beer data? This quarterly beer data. So what pattern have we not accounted for? This is the last question for this. We have removed the trend cycle. So the trend cycle has been removed. It's now centered at 0, which is a part of what we want for our residual plot. No clue. That's a great answer, Leo. 500 points for no clue. That's a great answer. Let me show it to you this way. If we go back to the original plot, what does it look like in the original plot? Remember that pattern you just saw a second ago? So if you look at this plot right here and look at the original data, the trend, the season, the remainder, what do the residuals right here look a lot like? The residuals look a lot like the what patterns. Look over there on the right. And the residuals look a lot like the what pattern. So here's the remainder right here, but those remainders look a lot like the what pattern. So the residuals in this model right here, after we've differenced it twice, look a lot like the what pattern over here. So it's quite clear that we did not account for this variation yet. We did remove probably the trend cycle. So we have accounted for that with the differencing of 2. But the residuals right here look a lot. Look at the boop, 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 boop. They like the flowy pattern through them. The season. That's right, Leo. And take a look with the residuals. Where's it spiking? It's spiking with a negative correlation with last year and a positive correlation. So that's like if last winter was high in beer sales, this winter will be high. If last winter was high in beer sales, next summer will be low. So they're negatively correlated with an interval of 2 off, which then it goes by every year. But they're also positively correlated with, like, if this summer is high, next summer will be high. If this winter is high, next winter is high. But then the seasons are negatively correlated. And you can see kind of the pattern right here of what we see with each year. Like Q2 in Australia for beer sales is generally low. and Q4 is generally high, and these are all the different years. That's what this plot shows, is the seasonality of it, that Q2 in Australia is where they sell the least amount of beers, and then Q4 in Australia is when they sell the most amount of beers. So end of the year, beer sales are high in Australia, and then right before winter in Australia is low. That's what this graphic is explaining. And there's a strong correlation, like there's a consistent high Q4, and that's why there's a 4-quarter trend right here. I do not know. Yeah, email Alyssa and tell me if you get that. And great work, everybody here. Really good review of 475. Lot done. Back to 201. We're going to do a lot of questions. Here we go. Thank you, everybody. That was a really good review of 475. Hopefully, 475, we love you. Get some practice right there. Good stuff. Know how to read those things. And always check out the book. The book has so much help because a lot of the questions are pretty tough. We're going to do the waiter waitress question first. Multiple people have asked about that. So, waiter waitress question. Waiter. I'm going to break my table. The waiter waitress question coming right up. Waiter waitress question. Here we are with the waiter waitress question. Let's do it. Okay. So this is the waiter waitress question. And what do we have right here? A waiter believes that his tips are slightly skewed to the left. Now that's important information. They believe they're slightly skewed to the left. I want that to go away. Really? That's a bummer. Oh, there it went away. Slightly skewed to the left with a sample mean, or rather true mean, and a standard deviation. Now, this is information we could give you on the test. What is the following describing about their tip population? This is telling you the what of the tip population that they're doing. 5-letter word that has told you the what of the tips that they're getting. The what of the distribution of their tips. So that's just told you the what of the distribution of their tips. Slightly skewed to the left. That has just told you the what of the distribution of their tips. Slightly skewed to the left. We will have the mean. The mean comes up next right there. Slightly skewed to the left is the what though. So you are correct, Leo. Slightly skewed to the left is the what of it. The shape. Christian, great work. Good to see you, Christian. It's the shape of the distribution. So if it's slightly skewed, you might say, well, then the sample size should be at least this. If it's slightly skewed, the sample size should be at least this. And don't worry, I know I don't have slightly skewed on here, but you could just cover your bases and say, well, it should be at least this. It's slightly skewed. So they say it's slightly skewed, so maybe we should have at least this. So look at the numbers here, and what do you think? 30, Christian, great work. So do we have at least 30? The sample size says the sample is 50. So that would meet the large enough n condition. So n is large enough. So it doesn't ask us to check the conditions here, but it's good review to know that since the distribution is slightly skewed to the left, we need a sample size of at least 30. That's a more than enough. And then our sample size of 50 right here definitely meets it. So we pass the 3 conditions as long as these are randomly selected, less than 10% of all their tables, and our n is large enough, which it is right here. Now, the next bit of notation, and great job, Leo, I think you're about to get into it. What is this? Now, be careful. Be very careful. I want you to tell me the colors of what these are, but also directly what these are. I know what it says, but be careful. It says the mean is 10.10. Tell me in notation what you would look for on the formula sheet. So it says the mean is 10.10. The standard deviation is 6.90. Because there's a lot of similar things, but tell me directly, because this is about the tip they're getting, a quantitative value. So these values here are directly what and what. So this is where usually there's a lot of similar stuff on the formula sheet, and someone's like, I don't know which thing I'm looking for. This is a quantitative question. So what should they be looking for? So what should they be looking for? It says the mean is 10.10. Good practice right here. The mean is 10.10. So much silence. Ah! So what would that be? So like if I go to the formula sheet here, let's bring up the formula sheet. Andrew, good to see you here. Oh, joining back in. Oh no, Leo, if you email me, Leo, and say, can you email her? I'll email her. If you remind me, I'll see if I can get it. Oh. Okay. Okay, cool. Yeah, so it said the mean right there. So what value is this problem giving us? What value is this problem giving us? I might even copy paste this over to here. I'm grabbing all this information. What value is this problem giving us? I'm not blocking anything important right now. It says the mean is $10.10. And you got your formula sheet right here. The mean is $10.10. I'm having people answer more questions because we're getting close to the test. I can solve the question, but we got to make sure everyone else can solve it too. It's not the sample mean, Kyra. Great answer right there. It's not the great Christian. It is mu. That is mu. And good work, everybody. This is mu. Good practice. Don't worry about getting it wrong, Kyra. We're throwing you 500 points. Do not worry about getting it wrong. This is your practice. Go out there on a limb and just put as many answers as you can. This is our practice right here. That is mu, which then it is the mean for the distribution of the sample mean. And then what is in green over there? What is that value? It says the standard deviation of their tips is what? So that value in green is what? So the value in green is what? So it says the standard deviation is that. It's not Wyatt. Good, Sally. Good answer. Good guess. Cool. Well, be very specific. Be very specific. Leo, you might be on the right track. I think you got it, Leo. But be very specific with what the notation is. Like if you get it on the test, you get it. Be very specific, and then I'm gonna highlight it. That value is what? So you'll see it in the formulas. And here we'll highlight. Well, it's sigma. Kyra, great job. You are correct. That is sigma. Yep. And so now we see what we need to do right here. Great work, Leo, too. Does everyone see what we're going to do? We're going to find the mean for the distribution of the sample mean. And we're going to find, that's what that says, the mean for the distribution of the sample mean and the standard deviation for the distribution of the sample mean. So we're going to plug in these values right here. The mean for the distribution of the sample mean is $10.10. So this value right here is $10.10 just because that is mu. Mu is that, so that is. Oh, Lexus, good to have you here. And then the standard deviation is going to be, what was the original standard deviation? $6.90 over the square root of 50. And so the new standard deviation, square root of 50, 7.07 or something. There it is. I've done that too much. And whoops. What was that? Oh, $6.90. There we go. 0.976. There we go. So these values will then be used to draw the what. Since we've met all the conditions, and we have a mean and we have a standard deviation, these values here will be used to draw the what. We could have to find for the z-score. That is correct. So we could have to find a z-score on the test. That is correct. Which the formula is right there. We are going to now use these values to do what? Which I can do on the David M. Lane, or I can do by hand to practice. Good practice. What do you think I'm going to do? What am I going to use the value of the mean and the standard deviation to do? What will Brian do next? Say is a mean, draw the curve. Christian, great work. So we're going to draw our normal curve right here that we have these values. We're going to put 10, 10 right here. And for right now, when I'm drawing this, I'm going to go right here and just use $1. I'm doing a rounded version to just draw it for us. I would not do this on the test with $1, but if I change this to just $1, because that's kind of close to, it's going to make it very easy to see. And then we're going to do it actually here in a moment. Now, this is a rounded version of the problem just to make it easier to understand the numbers. I'm just going up one standard deviation, which is close to $1, and then I'm going to put it in David M. Lane to get the actual numbers. So that's a rounded version. Let's put it here, rounded. We're going to show the David M. Lane in a second. But this is a rounded version of the problem where I rounded it to $1. Now, the question asks, he wants to make, it's a he this time, he wants to make on 50 parties, he wants to make $650. So how much on average would he have to make $650 on 50 parties? His average tip would need to be what? Like he's saying, I have 50 tables this weekend. I need to make $650. I will have to average what? I would have to average what to make this? So what would they have to average to make this? So you're saying, okay, I have to make $650. I've got 50 tables, $13 per table. Great job, Alexis and Christian right there. Excellent work. So that's the average tip they'd have to make is $13. And that's what they want to see as a sample mean. Does that make sense? Like they're saying, I have 50 random tables. I need to average $13 on average. Like my sample mean for these tables needs to be $13 for me to make $650. So what's the probability of that? Well, we can go over here to the David M. Lane. Well, let's draw it here first, and then we'll go to David M. Lane. Oh, how's it look for them? Does it look likely or not likely? Tell me likely or not likely. They need to make $13. Ooh, how's it look for that sample mean, that Y bar of $13? How's that look for them? Not likely, right? And you're like, nah, I don't know about that. You're over here. So I think this is not that likely for you to make that. Doesn't look that likely, right? So we're going to go to the David M. Lane. It's going to do the drawing. On the test, you would probably need to z-score that. And we'd go right here. We put in the standard deviation. We put in the mean of $10.10. This is the same drawing, just with the numbers carried out a little bit better. And then we want to see above $13. What, really quickly, the z-score is basically this rounded. What is the z-score of this basically? The z-score of this is basically what for 13? You can see it on the graphic. The z-score for 13 is basically this. If we had to find the z-score for this, I'd say, well, it's basically this. You can see it on the graphic right now. 13, and Leo's kind of saying it in the chat. Great job, Leo, right there. It's basically 3, right? So the p-value... No, I'm going one higher. P-value is going to be about that. So the probability of it, the p-value, is going to be about that. Let's go to above 13. It's that tiny little sliver right there. It's more than 0.00015. My guess is 0.003. It's exactly 0.0015. Well, rounds to 0.002. Close enough guess, right? Close enough guess. So the answer is this right here to the first question. And so make sure to put the mean and the standard deviation in the applet and solve for it. It's exactly that right there. 4 decimals. There we go. Rip to his tips. Yeah, it's not happening. I'd say it's not happening. That's not happening. But then he says, well, just tell me about the best 1% of my weekends. So to do the best 1% of the weekends, we have to go here to the second button. And we're over here. So we're going to take and copy this information over here and talk about the best 1% of weekends. Now be careful, because a lot of people go here to the best 1% and then they say they're going to make $12.37. This is their what for the best 1% of weekends. This is their what. Remember, this is not what they're making. This is their what tip for the best 1% of weekends, because this is not a distribution of a singular tip. This is on 50 tables, the what tip. So we went to the second button, we put in the mean and standard deviation, we asked for the best 1%, and this is not for one tip, it's the average tip. So since this is their average tip on 50 tables, what should I do to it? So I'd say your average tip on 50 tables on the best 1% of weekends is about $12.37. So I should take and do what to that value right here? Because that's their average tip on 50 tables on the best 1% of weekends. I'd say on the best 1% of weekends, your average tip would be about $12.37 on 50 tables. So to find out how much they make, what should I do? To find out how much they make, what should I do? Because that's their average tip on 50 tables. Because that's what that distribution represents. Like saying, here's what I'd expect for 50 tables. Multiply by the numbers of tables. Laura, great job. There you go. That's got it. And so that makes sense. They'd make about $618. That's good money right there. Man, I'd like to make that kind of money. We should have it. Don't you dare, Matt Pearson. 4 decimals, 2 decimals. There's no decimal on that. Boom, 100. Got a little worried since I didn't round those last decimals. Oh, I could do this in R and get decimal places you wouldn't even believe exist. You'd say, I didn't even know we cared that much decimals. Does this make sense? This is a tougher problem. But here's the thing. We're going to speed run this problem. If you get this problem down, what are the things you'd want to instantaneously know about this problem? We're going to do a speed run version of it. What is the most important thing for solving any of these problems in any of these chapters? Then we're going to do pregnancy problem next here. But what is the most important thing for solving any of these problems in any of these chapters? The most important thing will be knowing your notation and then knowing how to use the formula sheet. So if you have these problems down, here's how it goes. Right here, they're giving me the mean and the standard deviation. So let's go ahead and get our applet open. 2 seconds. I'm going to make it so we can see both at the same time on the screen. So you're going to see both things. Applet, same time on screen. Really? There we go. I'm going to make it so we can really do this problem. Okay, so I'm going to disappear off the screen here while I do this. We've got everything we need on the screen so you can see it all at one time. We've got here the mean and the standard deviation. The mean of his distribution is 8.70. It's not a he today. There we go. And then the standard deviation is going to be the original standard deviation divided by the square root of n. And we go right here and do 4.50 divided by that. New standard deviation obtained. New standard deviation. I think we're good on both the graph. Oh, there we go. We're good now. And now we want to do, they need to make, on 40 part is 350. So 350 divided by 40, there's that. So they need to make above this. And the probability, oh, I'm clicking on the wrong one. There we go. Oh, wow. So that's likely to happen. Okay, so that's very likely. And we got all the decimals we can get. And the best 10% today, so the best 10% would be this amount. And then we're going to take, and we're going to times that by, I think they're 40 tables. And there it is right there. And we should be good. Check answers got the 100. Great job, Leo. 100 points, Leo, practicing as we did this right here. Find the mu, find the sigma, find the sample size, know your notation. Please review the start of the problem where we did it a lot slower. And we went through and we marked all of our notation. At that point, it becomes going, I know, right? Usually my Pearson like goes some crazy route with it. But number one thing is know the notation. Know the notation, identify the notation, draw the normal curve, and then kind of answer the questions. So Alexis, thank you, Alexis, 100 points right there. Yeah, they do make it sound tough. And then it's like, know how to do it. Alexis, 500 points, Alexis. I'm hoping, I want people to get confidence to be like, I can solve this problem if I know the steps. Find the notation, solve for the mean standard deviation, draw the distribution, and then find the things. Human pregnancies, you got it, Laura. Let's do it next year. Thank you, everyone, for all that positive energy. It's, I hope no one thinks like, oh, he's just trying to show us that he can solve the problems. Well, I hope I can. I've been solving that same problem for 12 years. I'd love it if someone, like, if I got a problem wrong and if someone's like, do you know how to solve it? I'd be like, some days my brain just doesn't work. You'll see me get problems wrong. It happens all the time. Doesn't happen today, though. Not today. We're going to do the human pregnancy one. And so practice the problems. You can conquer them. They are tricky. It's easy to make errors. And don't worry if you make an error. We're here to practice. Okay, human pregnancy problem. Let's do it. Exactly. The formula sheet's going to be a huge help with the notation. So this problem is a bit interesting because, can you go over the conditions? Yeah. Well, Jalen, we got that. We'll talk about some conditions here. And then if you have another question, let me know and we can go back to it. You got it. So here we are. Assume that the duration of human pregnancies can be described by a normal model. So it's telling us the original distribution is normal with a mean of 264 and a standard deviation of 15. What's the first thing we're doing? We're doing it right now. What are we doing with this problem? We'll go and we'll even put this over here because this is going to be a huge help. So let me copy this. What is the first thing we do? Notation. Leo, another 100 points. Leo knows every problem we're doing is we're jumping in here and we're doing that notation. Jalen, we'll do that next right here. We'll do a little canvas content. So we're going to go back over here. We're going to take our problem and we're going to go grab it. And let's go do the notation on it. Okay. First thing we're doing is we're always talking about the notation. So what notation do we have here? Let's see if you can solve the notation for this question. It says human pregnancies can be described with a, so this is how long was your pregnancy? You just walk up to someone and say, hey, how long was your pregnancy? And they say, I'm taking Brian's stats class and say, of course. Brian. But what kind of question is that? If we're asking people how long was their pregnancy, what kind of question is that? Don't ask people that random question unless you know them and it's appropriate. What kind of question is that? What kind of question is that? That is a what question? Quantitative, exactly. Quantitative because it's a number. So we'll be dealing, and it'll be a little bit later, we'll be dealing with this stuff right here. So what values are given to us up there? What it says with a mean of 264 and a standard deviation of 15. And I pause because I think it's very easy for people to make errors on this. There's a lot of notation on the screen. We've narrowed it down to a quantitative question. But what do we have? Which one of these is it? What are those values? Correct, Christian. Can you go into a little more detail, Christian? I think you're putting the thing critical value. Ooh. Is that still in the homework? I'm eliminating that in a second, Cassandra. That'll be gone. How is this? Oh, because I've deleted it multiple semesters now. It'll be gone in a second, Cassandra. And I might have to like adjust grades or something, but it'll be gone. It won't exist. I'll have to tell Terry. I'll say, hey, that's still in there. Shouldn't be in there. Because that's a new thing. Or unless you're doing... Are you doing the next chapter 14? If it's so, that should be in there. So Christian, go into a little more detail. I think you got it. I'll show you the quick way to solve it, then I might remove it. It's actually giving us the right side, Christian. Good answers. It's giving us 100 points right there. It's giving us this value. And it's giving us that value. Does that make sense? Those are the values it's giving us. This is sigma, and this is mu, which then you can find the mean for the sample mean, and you can find the standard deviation for the sample mean. So it's actually giving you the right side. That value is mu, which is the true mean. So it's saying human pregnancies have this duration, average duration, and it's saying that the variation in human pregnancies is 15 days. So it's giving you both those values right there. Very important to know because there's a lot on the screen. It does say mean, but there's a lot of different mean words. How many questions are on the test? 40, 50-ish questions, something like that. I think it shows it if you click on the test. But yeah, 40, 50, somewhere. About same as test one. Good question to lay right there. And so that's the mean and the standard deviation. Okay. So with this information right here, let's look at the first question. Now this question kind of throws you for a loop. What percent of pregnancies should be between 275 and 280 days? Now, what's interesting... Oh, great job, Jameson, getting that 100. What's interesting about this is you can actually use the formulas right here. But if we're talking about a pregnancy, what is the sample size for a pregnancy? If we're talking about a pregnancy, what is the sample size for a pregnancy? So we're talking about a pregnancy. What is the sample size for? Yep, it's 1. And frankly, Rock knows. It doesn't matter. At that point, you're dividing by 1, which doesn't do anything. Does that make sense? So you're using the original distribution because that's 1 pregnancy. So the standard deviation does not get smaller. Does that make sense, Alexis? Because if you're dividing by 1, because you square root of 1 is 1, so you're not even doing anything right there. So to draw the original distribution, we're going to go here to the David M. Lane. Great job, Alexis. we're just going to take and draw the original distribution, which would be, I can draw this one a lot quicker. So it's 15. Draw distribution. 264. Go up, up, up. Down, down, down. And 279. 294. And let's go look at the David M. Lane. So 264 and 15. Okay. So we go right here and we put 264. We go to 15. And so we do that right there. There we go. Good stuff. So once again, you can sketch this out yourself right here. Once again, I'm just going up the standard deviation units and putting the mean at the center. And this is for a singular pregnancy. This is actually chapter 5 right here because it's just one observation. It's not the distribution of the sample mean yet. More to come on that in a second in this question. So when we look at this, it says, what is the probability a pregnancy, singular, 1, will be between 275 and 280 days? For that, we can go to the between right here and do 275 or 280. Now, on a test, we wouldn't have you calculate directly this. We might ask you z-scores related to this, but we could also draw this out or things like that. We used to have people draw it out, which we could have you always draw these things, like draw the, the between and show the area. We would just check to see if you put the mean at the center and the right standard deviations. We'd often supply a curve. So that way you didn't have to draw the normal curve because even I don't draw them perfectly. So you can see the probability is very small and it's only 8.86%. And let's make sure we have it entered the way it wants us to enter it, which is a percentage. So we need to move the decimal over and it says to 1 decimal. So we need to round up. Okay, nice job. It is uploaded to Canvas. Leo, great work right there. At least how many pregnancies how long should the longest 25% of pregnancies be? We're going back here to the normal curve, but we have to click the second button and go here to the longest 25%. Make sure it's showing the top 25% here, and it's going to be this number, 274 days. Make sure to put in your mean and standard deviation. I always put it in for both sides of this curve, the first and the second button, the mean and the standard deviation when using it. That way I can find numbers. And so we're going to go right here and do 1 decimal. Now, for the last few questions, it has changed. This is no longer the mean. I'm going to pause here. This is for the what? This is about how many pregnancies today? 60 pregnancies. And this is now chapter 14 because we're now actually doing what? We're now actually doing a what distribution because this is for, I think it said like 40 or something pregnancies. So this is no longer about a pregnancy. This is now the sampling distribution. A sample of women will be taken. And for this problem, we're looking at a sample size of 60 women. So what would the mean be for 60 women? This is where people usually get confused. Now, one woman is expected to have a pregnancy of 264 days. If you average together the pregnancies of 60 women, you'd expect their pregnancies to last how long on average? One woman is expected to have a pregnancy of 264 days. Well, Christian, you might be looking at yours, I think. You might be looking at your problem. 264. Because the mean is the mean. And let's look at the equation. The mean is the mean. So the mean is still the mean. But what will change? So now remember this is 60 women. So instead of the mean stays the same. What will change right here? What changes about the distribution? The mean stays the same. Hints for Canvas content. The mean stays the same. Because the mean is the mean. It's like 264. Well, then I'd expect 60 women to have a 264 mean. Well, then the standard deviation we'd expect for this distribution is going to get smaller by a factor of square root of n. So 15 over square root of 60. Square root of 60 is like 7 something. So about 2.2. I always do a quick estimate in my head. It's a little bit less. It's 1.93. If I get something, great job, Leo, right there. If it increases, the standard deviation gets smaller. So larger sample size, smaller standard deviation. And that's what we're solving right here. I always do a quick kind of solve in my head to see if I'm kind of close. I estimated 2.2. It's 1.93. But close estimate. As n increases, standard deviation decreases, which is part of the central limit theorem. The the distribution gets tighter and more normal. And so this is the new standard deviation. Now, once again, whenever I get these numbers, I immediately plug them into both sides of the applet. So make sure to had the wrong value. Plug in both values, and you'll notice your curve is now smaller. So the standard deviation has decreased now. And so with this right here, what is the probability of the mean duration for these 60 women being less than 259? Do I need to click button 1 or button 2 to find less than a certain value? Button 1 or button 2? Button 2 has me enter in percentages and tells me where that percentile is on the normal curve. Button 1 allows me to input values. And this question asks me, what is the probability of the mean duration being less than 259? Exactly. I need to go to button 1 to go below 259. And there it is right there. It's a very low probability. We're just going to take that value, copy, paste. Do we lose the streak? Oh my, look at all those decimals. No streak over. Woo! Get scared, I'm going to. Very unlikely, right? Very unlikely. Good work. And so I think we had a few more questions. What was the other questions? We had questions about canvas content, I think. Critical values. Yes, critical values was next. Go back to the main screen. Okay. Critical values. Then we got some condition stuff. Oh, I need to email class. Ooh, no, wait. They're 150. I got no time. Critical values. Is this... Let me go look. You think it's on the homework? I need to go remove that. I'm gonna check it out and then remove it. It's for after the test. I have deleted it multiple semesters. It needs to be deleted from our blueprint that we use. Let me go look at this. It's like, no, why? It's here. Let's go check it out. Okay, so this will be deleted in a moment right here, but I'm going to show it just to kind of talk through it for a moment. So it's going to find the critical value of a T with 23 degrees of freedom. Okay, you look at it. You think really hard on it. You say, okay, you say, brain. Come on, brain. No, brain. Come on, brain. No. Really? Really? There we go, got it. There we go. It's all done. Okay, let me show how it's done right here real quick, and then we're gonna delete this. Okay, whoops, wrong thing. You just gotta think really hard. You gotta be like, rah, rah, rah. T's are kind of like Z's. T's are kind of like Z's. Let me pull up another version of it. T's are nearly identical to Z's. So the reason I'm able to solve this, wrong thing right there. The reason I'm able to solve this is because I know Z scores off the top of my head, and T's are basically Z's. But I'm going to show how to solve this. And then we're going to delete it because it's not on this test. So what I was doing in the background right here in my head is I know the Z scores for things like a 90% confidence interval. Now, this is actually one of the toughest ones. This one I'd have a very hard time guessing because the Z score for a 90% confidence interval is 1.645. And no notes on the exam. No notes, Ford. Thank you for asking. No notes on the exam. You're allowed the formula sheet, but no notes. Good question, Ford. 100 points. No note cards on the exam. Don't do that. Don't know whatever you do. You're in trouble for that. Don't do it. This would be very, very hard to guess. If I got that, I'd be shocked. Because the T distribution, which MuBot has put in the chat right here, has with a value called in it the degrees of freedom. So some people are going to T applets or T tables, but don't go to a T table, go to the T applet. We'd put in right here 90% shaded, and there's the value. So if you're using the tables, you have to go through and look up the values, but we supply the value to you on the test, and we usually use applets to get the value. So this question right here, go to the T applet MuBot has put in the chat if you still are seeing it, but I'm going to delete it, but maybe you're in another section where they didn't delete it. So that's why I'm showing this. And now you could put in the value right here and round to 2 decimals. I don't want to go into too much further detail because it's not on the test. The reason I'm able to solve this one is because I know the t statistic for a 99% confidence interval, or excuse me, the z is 2.5758. So this is probably going to be about 2.6. The t is always bigger than the z, and I'm a little bit off, it looks like. Is it really a little bit bigger? It is. But once again, you would go to the t-applet, and you'd put in 99% confidence. 99% confidence means the middle 99% is shaded, and then you would enter in the degrees of freedom over here, and the degrees of freedom are 79. That tells us the shape of the distribution, and now we have 2.64, and I was close enough. So you need to go to the t-applet, enter in, here's the way to do it, go to the between, enter in the p-value as the percent you want shaded, and then enter in the degrees of freedom. Does this, Alexis, does this make sense? So 95% confidence, make sure it's between, degrees of freedom 23, and there's the proper t statistic. Alexis, does that make sense? You might be answering it right now. I'm going to delete this question. I need to delete it from both, so it's going to take a moment right here. I'm going to delete it from both sections. This question should not exist, and this is my second semester deleting it, I think. I deleted. I need to just go delete it from the blueprint that we use. And then it will no longer exist. How is this looking right here? Does this make sense to people? This would be your answer right here, Alexis. And enter in, make sure to go to the t-applet Mubot's put in the chat. Go to put in your p-value, which is going to be the area between it. Make sure you've clicked between. And then put in the degrees of freedom it tells you. And then this t-score right here, which is also over here, is going to be the proper value that you would enter in when it asks you for that value right here. And hopefully this has helped shown how to do it. But T's are basically Z's. More on them to come on test 3. So a good peek into the future. Head back over to the main screen. What questions do we have? I'm going to go delete this from our sections. It is open questions right now as Brian goes and fixes his assignment manager. Going in and deleting a question right now. Hopefully it doesn't mess things up. Let's see what happens. Uh-oh. We'll find out. Okay, remove questions. Wait, what? Oh, I clicked confidence interval question. Why do we have this? Put your questions in the chat. We got time for probably one more. Replace questions. Can I replace it? Won't let me replace it. I can actually replace it? Trying to find a new one here to replace it with. Putting something easy in. Okay. RA1. RA1, okay. Well, I didn't know I could do that. Learn a new thing every day. Fixing the last assignment over here. One more song. Okay. Fixing the other assignment. RA1. The question I put in is a very easy one. Replace question. Chapter 13. RA1. Okay. I think that's replaced it. Oh, did I have to done? Did I not do it? Oh, I bet I didn't do it for the other class. I bet I didn't click done. I hate it when things like that, when you have to click done and you do everything you need to do and then it doesn't click it. And then I go back and I'm like, I swear I did this. And I don't do it again. Let me see if I replaced that question for the other class. Sorry, I haven't looked at chat in a moment here. I'm just making sure getting this done. Oh, and it did replace it. Good. There we go. Which one's questions right here? Waist size is on chapter 14. That will be the last question, it looks like. Waist size is chapter 14. Here, what replaced in for this? Okay, waist size question. And Stat 201, chapter 14. Let's do some chapter 14 waist size question. Thank you so much, everyone. Great questions today. Great office hours. A lot of office hours tomorrow. And the waist size question. This is a good theory question. I really like the waist. Ooh, a lot of questions, chapter 14. There's more. Wait, I'm thinking we're in the wrong chapter. I'm in the confidence interval chapter. I literally looked. I was like, why are there so many T statistics? And that was Brian's like ultimate frustration. And I was like, what is going on? Why are there so many T statistic questions? We shouldn't have those yet. So I fixed it and everything's good to go now. The T statistic question should be gone. Now we're doing the waist size question. Okay. Here we go. Over here to the waist size question. Let's take the timestamp on it. 2022-42. Let's do this. Here we go. Do you think the exam questions surrounding chapter 13 are less difficult than the Pearson ones? I'd say so, actually. Like, the problem is we do a lot of theory questions, and I think this is such a great theory question for the test. So I think sometimes the ones we put on the test are easier, and people, you know, get so used to solving these Pearson questions that they're like, well, you know, these questions are so tough. But this first question is super easy, I promise you. Because if we know the formulas on our formula sheet, here it is, our formulas again. Let's just grab this and bring it over here to a new page. The mean for the distribution of the sample mean is what? Just tell me what the mean for the... Read the formula sheet. We're doing the distribution of the sample mean, chapter 14. The mean for the distribution, it stays the same. And that's some theory questions on the test also. The mean doesn't change. That's on the Canvas content. So, Leo... What is the first answer right here? The theoretical mean, which is what we would expect the mean to be, should be what? The question says that men have a waist size of this on average and have a standard deviation of their waist size of this. So the theoretical mean should be what? Now, this is what we see in a simulation. And then the sample size right here, say it with me. You know what I'm about to do. The sample size, because the mean is the mean. It doesn't matter. And that's the formula that the sample mean, the expected sample mean, so that's expected sample mean is equal to the mean. So since we know what the mean is, that's the mean. This is the expected. Now, this is what we see in a simulation. Don't even look at that. Don't even look at that. That's just a simulation over there. That's someone saying I simulated values and saw what I saw. And look, these values are kind of close. Weird that that one's so off. They're trying to trick you. But that's a simulation someone did. Don't look at it. We'll look at that here at the end to see if our values are close to the simulation values. But if the mean is 36.24, then the sample mean of a certain amount of two waist sizes sampled should be about 36.24. Now, the standard deviation of the original population is 3.96. But the standard deviation will get water. So this 3.96 will need to be divided by what over here? So the 3.96 will need to be what? The 3.96, there's where the 3.96 would go. It's going to get smaller by a factor of square root of n, right? So if you're wondering what I'm doing for all this, every time I solve one, I'm going to take 3.96 and divide by square root of whatever n is. So exactly, 3.96 divided by square root of n, so it's going to get smaller. And you can see that over here. Now, remember, this is a simulation. It's giving us estimates. It's not the truth. We're saying theoretically what it should be. Like, theoretically, this is what we should see in the simulation. It's not saying we will see it. It's just going to be close to it because simulations aren't perfect. But they do kind of show us what we would expect to see. So we're going to take square root of 2, 3.96 divided by that. Be very careful and do decimal place accurate to 2 decimals. Once again, I'm going to take 5 and do square root of it. Copy it. 3.96. Careful. Divide by it. 1.77. Then I'm going to do 10. Take square root of it. 3.96 divided by that. 1.25. Then I'm going to take 20. Really? 20, square root it, and take 3.96 and divide by it, and there we go. Exactly. These should all get smaller, and they should kind of be close to these values. If your values are very far off, which they should be, they're probably not going to match exactly. But are my values kind of close to these values over here? Are my values kind of close? Not perfect, but are they kind of close? Like, is that 0.89 close to that 0.88? Now, don't make it that 0.88. Don't change it. Don't be like, well, I should make it that. They're kind of close. And that these are the theoretical of what we would expect to see according to the formula right here, that the original standard deviation divided by the square root of n is the standard deviation for that sample size. Once again, second rule of the central limit theorem, that the standard deviation gets smaller as the sample size gets bigger. Distribution also gets more normal, first component of it. So this are close. That's right, right? No. Good. Looking at the ooh, scary. So I'm scared. We're gonna lose our streak, Leo. Email me if you get this one wrong. This is a nonsense question. This is so much of a... I think it makes it clear down here on the bottom. It is 5, all right? Because at the bottom it says the distribution of the original data is nearly unimodal, nearly symmetric, so it does not take a very large sample size. So the more skewed it is, the larger n needs to be. The answer is going to be 5. Leo's probably done it. That is the right answer. That one's caught me off guard many times. I do not like that question. No, sir, I do not like it. But do remember from today in class, as we talked about. Now, once again, here's the thing. These notes are from my Pearson. These are the my Pearson notes. These are the my Pearson questions. They're kind of going to some of the subjective gray areas in this where, like, these are like standards like normal, skewed, very skewed. So we're in this range right now of like pretty normal. So you could say right here, you could just add another line of n equals to 5 if pretty normal. And that's just where it gets a bit ridiculous. And I just think, you know, you need more clear cutoffs in like Stat 201. So that's what they're doing right here, is they're choosing an in-between ground on this. Does that make sense, Leo? Is they're saying, it's kind of normal. So n does not need to be that large. If it was skewed, n would need to be 30. If it's very skewed, 100. If it's ridiculously skewed, 200. Because you can make another bound like, what if it's super duper skewed, and then 200? What if it's super duper duper skewed, 500? But the more skewed it is, the larger n needs to be. That's the concept here. And that's the important thing to know, that if it's normal, sample size of 1 is fine. If it's kind of normal, but needs a little help, then it needs a little bit of an n. So the more skewed it is, the larger n needs to be. And it's not the biggest fan of it. I've gotten it wrong before. And it's just kind of hard to tell. But someone might say at 10, like, I bet if I showed this to 50 statisticians, I would love to see. I should send this out and say, at what point is it normal? I first thought 10 all the time. I said 10. And 5's pretty good. I bet you some statistician might say 2. They might say that's normal enough. This is basically normal. I'll use a normal technique. Close enough. Most things don't even look that good. So 10 just looks so nice. 5's looking good, but Binwitz, someone might say, show me the QQ plot of the Shapiro-Wilk on that. That's probably what a statistician would say. Show me the omnibus test. Darn you statisticians with your statistical test for normality and p-values. But that's probably what they would follow up with. Show me the Shapiro-Wilk or the QQ plot. Anyways, I don't know. Well, with that, great job today, everybody. Good conversation. That top one's not normal, though. That's left skew. I don't think statisticians would. I don't know. We'll go talk to some. With that, we'll be back here doing class in 19 minutes. If you're in class, I'll see you then. Bye for now, everyone. Bye. Check your Discord DMs. Will do, Leo. Thank you, Leo.